Let's continue the exercise of the chapter Electrostatic Potential and Capacitance. Question 17. A long charged cylinder of linear charge density lambda. Okay. Linear charge density lambda. The inner cylinder we have to see there. Lambda is surrounded by a hollow coaxial conducting cylinder, red in color. What is the electric field in the space between two cylinders? Okay, so we take a point here, a point, say field point P in between the cylinders, and that field point P is at a distance r from the center of the inner cylinder, who is having the charge. So we can assume that the inner cylinder is having charge Q, so that the outer cylinder charge minus Q will be induced. Now, imagine a Gaussian cylindrical surface of radius r in such a way that the field point P is on the surface of the Gaussian cylinder. Now, we know that if you imagine such a Gaussian surface, then the electric flux passing through the cross sections is 0, and the electric field through flux through the curved surface only we need to consider. For the cross sections, electric field will be 0 because direction of electric field and direction of area are perpendicular. Therefore, in cross section there is no electric field. Now, coming to the electric field passing through the curved surface, we can apply Gauss law. So we have closed integral E dot ds is equal to Q divided by epsilon naught. Now as I told you, we need to consider only the curved surface. So we will get integral through the curved surface, electric field will be constant. So we can take outside integral ds is equal to Q divided by epsilon naught. That is E into the curved surface. If r is the radius, L is the length of the cylinder, then the area of the curved surface will be 2 pi r L. So E into 2 pi r L is the surface area of the curved surface of Gaussian surface is equal to Q divided by epsilon naught, but Q is equal to lambda L divided by epsilon naught. Will cancel on both sides, so you will get E is equal to lambda divided by 2 pi epsilon naught r. E is equal to lambda divided by 2 pi epsilon naught r, or we can multiply and divide the equation by 2. You will get 2 lambda divided by 4 pi epsilon naught r, and be taken as the final equation for electric field between the two cylinders. Now, next question 18. Hydrogen atom, electron and proton are bound at a distance 0.53 angstrom. 1 angstrom is 10 power minus 10 meter. So 0.53 angstrom is the distance between electron. Electron means plus E. We can take it as Q1. And proton is plus E, take it as Q1, and electron is minus E, take it as Q2. So two charges separated by a distance 0.53 angstrom. Estimate the potential energy of the system in electron volt. Potential energy you are asked to calculate in part A. potential energy U is equal to potential energy of the system. Our formula is 4 pi epsilon naught Q1 Q2 divided by R. Q1 Q2 divided by R. Here Q1 is equal to E and Q2 is equal to minus E. But at the same time, it is given in the question. Estimate the energy of the system in electron volt. If you just substitute the values here, you will get the answer in joule only. Joule you have to convert to electron volt, for which you have to divide the equation by E. So when you solve the equation, actually one of the E's will be cancelled. So rest of the part you can solve so that you will get the answer. The answer will be approximately minus 27 electron volt. You will get minus 27 approximately electron volt. Now that's the answer to part A. Part B, what is the minimum work done to free the electron, given that its kinetic energy in the orbit is half of the magnitude of potential energy. Okay. So there is a bound system. Being a bound system, okay, come to the answer to part B. It's a bound system. For a bound system, we know the kinetic energy, potential energy, total energy relations and all, okay, and the minimum total energy must be zero. Minimum total energy must be zero for the electron to escape from the bound system. And how much is total energy? Okay, so we know the relation between kinetic energy, potential energy and total energy. If total energy is minus U, then kinetic energy will be U and potential energy will be minus 2E. That's the relation connecting kinetic energy, potential energy and total energy. Now in magnitude, total energy and kinetic energy are equal, and that you need to make zero. So then here you will get a potential energy in the part A, so that we can say kinetic energy will be minus 13.5 electron volt. Sorry, kinetic energy is positive always. Kinetic energy is 13.5 electron volt. Now we want to make the total energy zero. What do you have to do? The total energy is already minus U. So to make it zero, you have to supply an energy plus 13.5 electron volt. So that total energy becomes zero. So total energy zero means electron can escape. So what should be the amount of energy we need to supply in this case? You need to supply positive 13.6 electron volt of energy. So that this positive 13.6 and the total energy here minus 13.6 electron volt. When added, the total energy becomes zero, so that the electron can escape. So answer is minus 13.6 electron volt. Now come to the part C. What are the answers to A and B above if the zero potential energy is taken at a 1.06 angstrom separation? In the first part, it is given zero potential energy is taken at infinity. Potential energy is zero at infinity. Now you are asked to take potential energy at a 1.06 separation as zero. So you know the situation that potential energy depends on our reference point. For example, when you calculate gravitational potential energy, you can take height from the surface of Earth or from the surface of a floor of a building or surface of a table. It's our discretion, the height, any reference point we can take. The same way here in this chapter for a potential energy, every time we define work done to bring the charge from infinity to that point, because we have taken potential energy at infinity is 0. Now, instead of taking infinity, what you are asked? You are asked to take 1.06 angstrom separation is having potential energy 0. So what you have to do? First, you have to calculate potential energy at 1.06 angstrom using the same potential energy formula 1 by 4 pi epsilon naught q1 q2 by r. R you have to take a 1.06. So in such a situation, you will get the answer around minus 13.6. Minus 13.6 electron volt. And this minus 13.6 electron volt question says that take as 0. So see the potential energy in the first condition. U is equal to minus 27 electron volt you got. Now minus 27 electron volt means we can write as minus 13.6 plus minus 13.6. Now potential energy at 1.06 angstrom 0 means this minus 13.6 becomes 0. So what happens here? One of the minus 37.6 you have to take as 0, because question says that potential energy for a distance 1.06 has to be taken 0. If so, what is the potential energy in part C? The potential energy becomes, what remains there? Minus 13.6 will remain there. One of the minus 13.6 becomes 0. So this will be the answer to part A if this condition energy is taken at 1.06 separation 0. Okay. Now what happens to the answer to part B? In part B, you see what happens. I told you have to give energy to the electron which is equal to kinetic energy of electron. Then total energy becomes 0 so that you can make the electron free. And think about kinetic energy. Kinetic energy depends on mass and velocity. It does not depend on our reference point. As it depends on mass and velocity of electron, whatever reference point we have used for calculating potential energy will not affect the kinetic energy of electron. Therefore, answer to A we have calculated already. Answer to B, there is no change. So no change for part B answer. Whatever reference point you have taken for potential energy, that remains plus 13.6 electron volt. Okay, now come to question 19. One of the two electrons of hydrogen molecule is removed. What remains? Two protons and one electron. So we can represent like this. So two protons plus E and plus E separated by a distance of 1.5 angstrom. 1.5 angstrom. And one electron. One of the electrons is removed. Electron is 1 angstrom. Determine the potential energy of the system. Okay. So now you can take it as Q1, Q2, Q3. And the formula, potential energy of a system of 3 particles. U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q2 Q3 divided by R2 3 plus Q1 Q3 divided by R1 3. Now here when you substitute charge of electron, you have to substitute minus E, and the final answer you can calculate in electron volt, for which you have to divide the entire equation by E, so that in each time one of the E's will be cancelled, so it is easy to calculate. So find the answer. Now question 20. Two charged conducting spheres of radii A and B. Two spheres A and B connected to each other by a wire. What is the ratio of electric fields? So in the first chapter we have studied two identical spheres, charged spheres connected with a wire. Okay, so what happens in such situations? We have taken the charge flow is obtained until both the spheres are having same amount of charge. But here the spheres are not identical. When the spheres are not identical, we will get the flow of charge until or the potentials of both the spheres are equal. V1 equal to V2. Not the charge becomes equal, but the potentials becomes equal. So we can take a V1 equal to V2. V1 equal to V2 means 1 by 4 pi epsilon naught QA divided by A is equal to 1 by 4 pi epsilon naught QB divided by B. Simplify the equation, then find the value of QA divided by QB. QA divided by QB is equal to A divided by B. Now, next, electric fields we have to calculate. Electric field E1, the first sphere, is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught QA divided by A square. And E2 is equal to again 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught QB divided by B square. So find the value of E1 by E2. Find the value of E1 by E2. When you calculate the value of E1 by E2, there one QA by QB will come. QA by QB you can substitute from here A by B, so that you will get the value E1 by B2 is equal to B divided by A. Is the first answer. Then use the result obtained to explain why the charge densities on the sharp and pointed ends of a conductor is higher than its flatter ends. So here the charge density we can take. The formula is sigma divided by sigma is equal to Q divided by 4 pi R square. A pointed end you can consider as spherical, approximately spherical. Pointed end, R is the radius of the spherical part. So when very highly pointed end means R is very small. R very small means sigma is very large. As R is small, sigma is very high. That is what we have applied in the case of the lightning conductors and all. You can see a lot of pointed ends in the lightning conductors. Okay, so that purpose of having the pointed end, at the pointed end we can have very high charge densities. Now next, question 21. Two charges minus Q and plus Q are located at a 0, 0, A and 0, 0, 0 minus A and 0, 0, A. So here two charges separated at a 0, 0, A and 0, 0 minus A. So you take like this Suppose this is Z axis, and 0, 0 minus A and 0, 0 plus A. 0, 0 minus A, we can have a point here minus A, where the charge minus Q is placed, and here we can have a plus A, where charge minus Q is placed. Now, here we can take another point. We can take an arbitrary point there. For that arbitrary point, so Z axis, take an arbitrary point where coordinate is Z. So here coordinate is minus A, 0, 0, here plus A, 0, 0, here Z, 0, 0. So we'll take an arbitrary point. Okay, we can give the name point A. Now, what is electrostatic potential at points 0, 0, Z? What is the electrostatic potential at that point? That's the question. So electrostatic potential at that point Z, we can calculate like this. Potential V is equal to first the potential due to negative charge. It is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught minus Q divided by 1 by 4 pi epsilon naught minus Q divided by Z plus A. So here, from origin O to the point A, distance is Z, and from O to charge minus Q, again distance is A. So it is an arbitrary distance A. So total distance from minus Q to Z means Z plus A. That is a potential due to negative charge. The same way now we need to calculate potential due to positive charge also, 4 pi epsilon naught plus Q divided by Z minus A. The distance between plus Q and the point A is Z minus A. Plus Q and the point is Z minus A. Now simplifying, you will get the total potential. Again, when you simplify, you have to take common factors out, take LCM. We have done already in derivations. Then you will get a 2AQ in numerator. That 2AQ you have to substitute as dipole moment P. So you will get the final equation 1 by 4 pi epsilon naught P divided by Z square minus A square will be the final answer. Now, that is only the part, okay, electric potential at 0, 0 Z. Then next, at xy 0, a point xy 0. xy 0 means it is YZ plane, and Z coordinate 0 means this plane is passing through the origin. Now for this dipole minus Q and plus Q, this plane is the equatorial plane. As it is equatorial plane at xy0, at xy0 means it is the equatorial plane of the dipole, and you know at the equatorial plane of the dipole potential is 0. Now next, come to part B. Obtain the dependence of potential on the distance r of a point from the origin r by a much greater than 1. This is an arbitrary point at a distance r. It's not mentioned it is in the axial line or equatorial plane. Okay, therefore at any point we have to take this derivation we have done in the theory. Electric potential at any point of a dipole. That derivation you have to do here, which you have studied in theory. Then next, part C. How much work is done in moving a small test charge from a point 500 to minus 700? A test charge is moved from a point 500. 500 means it is x-axis, that is the initial point, to minus 700, minus 700, negative x-axis, minus 700. And we know the potential, initial potential and final potential both are 0. There is no potential difference. As there is no potential difference, we can say the work done is equal to 0. There is no potential difference. Initial potential difference and initial potential and final potential are equal. Then, does the answer change if the path of the test charge between the same points is not along x-axis? Suppose it is not traveling along this straight line. Do you get the same answer or different answer? Suppose it is going like a path. Will you get the same answer or different answer? Again, answer will be same, because we know that electrostatic force is a conservative force. The work done in this force or work done by this force depends only on initial point and final point. It is independent of the path followed by the object. Therefore, you will get the same answer. Now, next, we can see the diagram. Electric quadrupole. Dipole means 2 charges. Quadrupole means 4 charges. You can see plus Q. 2 minus Q's are there. Again plus Q. At point P, at a distance R, we need to calculate the potential. So directly we can go with the formula. Total potential V is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Then we have to take the first charge in the leftmost side, Q divided by R plus A. Q divided by R plus A. Next, 2 charges are there, so we have minus 2Q, both are negative also. Minus 2Q divided by the distance is R. Then next, plus the charge in the right side, Q divided by R minus A. Now you have to take LCM, then simplify the equation, use the identities, and in denominator you can neglect the A square. You'll get an A square in denominator, taking R by A, and taking this condition R by A much greater than 1. Then you can see the relation here, V proportional to 1 by R cube. You will be asked to prove this. V for a quadrupole, V proportional to 1 by R cube. Okay. So you have to take LCM, simplify the equation. That's all. And just find what is the relation between V and R. Now, next question 23. An electric technician needs 2 microfarad capacitor. The required capacitance is 2 microfarad. Available potential difference is 1 kilovolt, that is 1000 volt. Available capacitors are only 1 microfarad capacitors, and maximum potential difference that can be sustained by a capacitor is 400 volt only. We know how you can make 2 microfarad capacitor from 1 microfarad capacitors. It's very simple. You have to take 2 1 microfarad capacitors, connect them parallel. So you will get a 1 plus 1 2 microfarad capacitor. But see the situation, what happens there. Available voltage is only 1000 volt. 1000 volt. The maximum voltage, if you connect like this, then each capacitor will get max 1000 volt, but the capacitors can sustain only 400 volt. So then what will happen? This kind of a connection is not possible. So we need to think now series, parallel, and all. Okay. So here we assume that n capacitors are connected in series. N capacitors connected in series. So when n capacitors are connected in series, we can calculate the potential difference across each capacitor. Potential difference across each capacitor. Potential difference across each capacitor is equal to, in series connection, the potential will be distributed. So we have n capacitors in series. So total we have 1000 volt. N capacitors are there. So each capacitor will get a voltage 1000 divided by n. And the maximum possibility is 400. Maximum that can be sustained by a capacitor. Therefore, what is the value of n? N you will get around how much? 2.5, but you cannot connect 2.5 capacitors. Either you can have 2 or you can have 3. Suppose it is 2, then voltage becomes 500, which is not possible. Therefore, the only option is 3 capacitors. N is equal to 3, which means you have a series connection in which 3 capacitors connected like this. 3 1 microfarad capacitors. Now, let's calculate what will be the capacitance of a particular series. Capacitance of a series. So here, for calculating capacitance of a series, what you have to do, it is a series connection. You have to take 1 by C is equal to 1 by C, 1 by Cs is equal to 1 by C plus 1 by C plus 1 by C, 3 capacitors. So you will get a 1 by Cs is equal to 3 by C, or Cs is equal to 1 divided by 3. That means microfarad is the capacitance of one series. Okay, so we have 3 1 microfarad capacitors. Effective capacitance of this particular series will be 1 by 3 microfarad. 1 by 3 microfarad. Now, next we assume that we connect identical series like this. Again 3 capacitors. Again next to 3 capacitors. So like we can take m number of rows. Total m rows. Assume that m such rows are there. If m rows are there and each row is having capacitance 1 by 3, and they have connected parallel, these rows are connected parallel. Parallel means direct addition. So how do you calculate the total capacitance? 1 by 3 plus 1 by 3 plus 1 by 3, like that. So the total capacitance of m rows, the total capacitance is equal to m into, so it is 1 by 3 plus 1 by 3 plus 1 by 3, etc. m times either, which means m into 1 by 3 is equal to V1 2 microfarad capacitor. The total the required capacitance is 2. Therefore, m is equal to 6. So how many rows are there? 6 rows are there, and in each row we have 3 capacitors are there. So 3 capacitors, such 6 rows. Therefore, total number of capacitors required to make 2 microfarad capacitor using 1 microfarad capacitor to have a voltage of a voltage of 1 kilovolt is 18 capacitors. We need 18 capacitors. Now, next, come to question 24. Voltage. Here we need a 2 farad capacitor. Distance between the plates D is given. Then we need to calculate the capacitance of the parallel plate capacitor. So we can have C is equal to epsilon naught A by D. Epsilon naught A by D. And you are asked to calculate area. So cross multiply this equation, you will get area of the capacitance. A is equal to CD divided by epsilon naught. And it's a big capacitor, 2 farad capacitor. Okay. So when you calculate the area, you get very large area. Okay, maybe in terms of kilometers like that. Very high value you will get. So it's not possible to construct such capacitors practically, but we need capacitors of high capacitance. But for that sense, we cannot construct a capacitor having area in terms of kilometers. So what do we have to do then? What is the option? We have to think about the electrolytic capacitors. So what is that electrolytic capacitor? You know, a capacitor means the capacitor plates are there, and between the capacitor plates we have the dielectric slab is there. If you can reduce the value of D, means the thickness of the dielectric slab between the plates of the capacitor, you can increase the value of C. It is not practical to increase the area A. The only option, if you want to get a very large capacitance, what do you have to do? Reduce the value of D. How much or how can you reduce? The option is that here you can have a very thin layer of certain materials with the help of the process like electrolysis. You know, electrolysis, you can deposit a very thin layer of atoms over another atom. So such methods we can use here. Okay, and very thin layer of dielectric material just separating the two plates. So that value of D will be extremely small, making large value of C. So that is what we mean electrolytic capacitors.